Hi there, this is a follow-up on my repair of the HP5334B frequency counter some time ago. The counter is working great, but it has only the standard 10 MHz time base. This video is about upgrading it with an ovenized reference standard on the cheap. The original oven oscillator circuit from HP is quite a beast, and even used ones still command a premium price. It lives in a metal can and is to be plugged into a connector of the main board. You also need to move one capacitor to switch the counter's 10 MHz time base from the standard oscillator to the ovenized one. Here's a part of the main board schematics. Two things I want to point out here. First, up here is the standard oscillator. Its output goes via capacitor C8 to the rest of the counter, which isn't shown in this section. The ovenized oscillator would plug in on the left into what is labeled OCXO socket. It delivers a 10 MHz signal on pin 1 and it connects via C100 to the rest of the counter. Of course, the counter can't have two 10 MHz time bases at the same time, so HP says to remove C8, which kind of abandons the internal oscillator. It still runs, but its output is going nowhere. If you try to find C100 in the parts list, you will search in vain. It's actually simply C8 moved into a new position. Secondly, if you look closely at the power supply circuit, you see that the transformer and the upper rectifier are always on. What looks like a switch on the primary side is actually the voltage selector, which just picks the right primary winding configuration for your mains voltage. The front power switch is this one. It's on the secondary side and only affects the second rectifier, of which you see a portion on the very right. That rectifier drives the actual counter electronics. The first rectifier is always running as long as the mains plug is connected to mains and it produces the power for the oscillator oven. It is labeled as plus 15 volts unregulated oven supply, and you find it reappearing on pin 14 of the OCXO socket on the left. All this means, of course, that the oven will always be on, so the oscillator will be on the right temperature and thus frequency immediately when you turn on the HP5334B using the front power switch. That may be okay if you're using the counter on a daily basis, but I'm not, and so in my setup the mains cord is connected to a switched socket which is usually off, and the oscillator will be stone cold most of the time. As a consequence, I will have to wait for the oscillator to heat up to be stable after switching on. A final note, there is this section here called Oven Oscillator Fine Adjustment. It delivers an adjustable voltage to the OCXO socket, but this is only useful if you have the original HP oscillator plugged in. Well, I won't. Instead, I'm using this eBay ovenized oscillator. I have been permanently running it for a year or so, and you have seen it a few times as a convenient target in my reviews of thermal imaging cameras. The item in the silvery box is the actual oscillator and its oven, and these are often harvested from old equipment before being put on these PCBs and sold. That's good, because new oscillators would drift while they age. Just in case, I have let mine running, checking the frequency occasionally, and it's as stable as I can measure using a GPSDO as reference. The seller I bought mine from doesn't exist anymore, but you find them all over the internet. Just look for these keywords. Of note is the 5V regulator on the left lower corner. The writing on the PCB says the module can be powered by 9 to 13 volts, and I have been running it with a tad over 9 volts, and even with that the regulator and polarity protection diode get hot, 60 to 70 degrees. The reverse engineered schematic is widely available on the internet. Apart from the hot regulator, the other issue is that because of the aged modules, the adjustment voltage range produced by this circuit is often not enough to pull the oscillator to 10 MHz. This was also a problem on mine, and there are various articles and YouTube videos on the internet on how to replace some resistors to make it work. The latest one I saw on this was from the DevProm a couple of weeks ago, so please go and watch his excellent video or any of the others out there, since I'm not repeating the fix in this video. With that out of the way, my first task was to look for C8. This wasn't as straightforward as you would think, because my PCB is a slightly different revision from the one in the service manual. From the schematic, the leg of C8 that isn't connected to the internal oscillator should be directly connected to the contacts of the switch that allows sending the 10 MHz to an output on the rear. And yes, I found C8. Sorry, that white coax cable is blocking the view. Now, with that confirmed, the solder pad right next to it should be for when C8 becomes C100, and it should therefore be connected to pin 1 of the OSC socket. And indeed it is. Pin 14 of the OSC socket should have the always-on DC supply for the oven. Wow, 21 volts, so much for the 15 volts in the schematic. That voltage is way too much for my module. Since that was the voltage when idle, I decided to load it with a resistor to draw about half an amp, which is roughly what the oscillator will draw when cold. It dropped slightly, but 19.8 volts is still a problem. I tried putting a power resistor in series with the supply from pin 14 and experimented with various values. This is about the best case. When the oven is heating up, that reduces the voltage to around 9 volts, which is okay, but as the oven is reaching its set temperature, the power draw drops and therefore the voltage increases and soon becomes too high. Attempts to reduce that high voltage with increased resistor values causes the voltage at startup to collapse below what the regulator needs, and the oven never reaches its set temperature. There is no way around it. I need to pre-regulate that oven voltage. Since the oven voltage is against ground, I can use the chassis as a convenient heatsink for a standard 3-pin regulator chip, and here you see the mounting hole I drilled between two labels so it doesn't ruin the looks. The same hole on the inside. The counter is standing on its side because that way it takes up less space on the bench. The idea is that a 9-volt regulator will fit right there and tame the oven supply voltage down to something the module can handle. I considered using a 5-volt regulator and bypassing the one on the module, but I had quite a few spare 9-volt regulators in the parts bin, so that's what I'm going to use. The module needs to be prepared. I soldered a wire to the 10 MHz TTL output and 2 wires for ground and 9 volts. I could have used a barrel jack, but I think a direct solder connection takes less space and is more reliable. To do the C8/C100 modification, I simply snipped off the leg of C8, moved it over to the other pad and soldered it to that one. That fix did not require taking out the main board, which would have required a lot of work. I also prepared the regulator. I bent the legs to give it more clearance from the stuff below. The 0.33 microfarad cap between input and ground is as close as possible as recommended by the datasheet. And there it is, installed with a bit of heatsink paste to the rear wall of the enclosure. The module is held in place by a tie wrap that goes through convenient holes in the motherboard PCB. It does look odd, but it works very well. I did say this project is done on the cheap, didn't I? The wiring to the OSC socket. I only soldered to the rear, so the socket itself is unblemished and still usable. From the top we have the thin wire carrying the 10 MHz signal. I should probably shorten that, but it works as it is. The black wire is ground. The yellow wire is the 15 to 20 volts DC from the power supply going to the regulator input, and the red wire coming from the regulator output carrying the 9 volts DC to the module. Here's the whole thing again as sort of a schematic, although it's hardly deserving that name. Yellow is the input to the regulator, while red is the 9 volts output. The 10 MHz output is tapped off the module and fed to pin 1 of the connector. The rest are just ground connections. To test it, I connected a 10 MHz signal from my Leo Bodnar GPS discipline oscillator as an input. The counter has been totally off for many hours. Turning mains power on and the standby LED and the oven starts heating up. Turning the power on for the rest of the counter, and after its self-test it displays the frequency, which is shown too high because the internal 10 MHz is still too low. But as you can see, it's rapidly catching up. In fact, overshooting somewhat, because now the display is too low, that is, the internal oscillator frequency is slightly above 10 MHz. But given a few minutes, it settles to an accuracy of 0.1 Hz, which is rock solid. I have not bothered to trim it yet, as I want to collect a bit of data how the module behaves in its new place over the next couple of months. But as it stands, the counter is totally usable and way more accurate than it was with a standard oscillator. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.